Still malinaw eh. Yes. Wala. It's just a Russian vehicle.
Welcome back, everybody.
It's
Welcome back. Ready? All right. So we're going to continue with our chapter number 26. We should be done by the end of today. And so we're going to we introduced the battery last time, which is a device that maintains a potential difference between its ends. And then we're going to introduce the concept of a capacitor, which we already know. So once we knew the infinite sheets of charge, we kept calling them parallel plates or capacitors. Okay. And then we're going to make combinations of capacitors. We will set them to be in parallel, or in series. Those are the two main combinations. We're going to talk about the energy stored in a capacitor. We're going to mention what happens when you put some kind of a material between the plates of a capacitor. That's the end of this chapter. Okay. So let's see. Charging or the concept of capacitance. Okay? Capacitance. Capacitance is defined as follows. By definition, it has a symbol. You have to give it a symbol. And as you might expect, capacitance starts with the letter C, so the symbol is C for capacitance. And it's equal to the charge that you can put on each plate of the capacitor, if it's parallel plates, over the voltage between the plates, over V, the voltage between the plates. I'll put a small subscript here, C, meaning the potential difference between two plates. So, for example, if you have a parallel plate capacitor, here is one plate, here is the other plate, and I'm looking at sideways, right? The plates, of course, are surface. And let's say this plate is charged to charge Q, and this one will have charge minus Q. Charge minus Q, and there is a potential difference between them. So if this is 0, this would be VC, right? That's the potential difference between. So capacitance is defined in this manner. Okay, that's by definition. It turns out that capacitance would just, after you divide things out, Q should cancel, and you should just have a geometric quantity, something that depends on the dimensions here. So for instance, let's say the distance between the plates is D, and the plates have an area A. Let's say the plates have an area A, right? They have an area A. So let's try to follow this expression and see what we get. So parallel plates. I emphasize the formula I'm going to derive right now only applies for parallel plates. You can have other geometries, but the most common one is this parallel plates. Okay. So we get C is equal to Q. Let's say I put Q on the plates, right? Each plate has a charge Q over the potential difference between the plates. Remember what the potential difference between the plates was. It's the electric field between the plates. Here's the electric field, let's say, times the distance between the plates, right? E times D. So the potential difference will be the electric field times the distance between the plates. So I get Q is equal to, Q over. Now remember what the electric field between two parallel plates was. What was it?
Eta over 2 epsilon naught?
Yeah, it was eta over, each plate contributes over 2 epsilon naught, so when you add them it becomes over epsilon naught, and then times D, right? And eta is Q over A, right? It's the charge over area. So you will get this, Q over, eta again is the charge over area, so capital Q over the area, and I have the epsilon naught at the bottom, and then I have D here, and the Q we cancel and you flip the expression, and it ends up being this, C is equal to epsilon naught times the area divided by D. That's the capacitance. Parallel plate capacitor. Now the units, if you look at it, the units will be, what are the units of charge?
Coulombs.
Coulombs. Units of voltage?
Volts.
Volts, yeah, and a volt is a joule per coulomb, right? So technically it's just coulombs per volt. That's it, coulomb per volt. So, but nobody calls it a coulomb per volt, it's called a farad. So the units are farads. 1 farad. So the symbol for a farad is F. Now again, does this formula apply all the time or just for parallel plates?
Parallel plate.
Only parallel plates. We will do a cylindrical capacitor and we'll do a spherical capacitor. At least that's the plan at the end. And you will see it will be a geometric quantity, but not necessarily, it will not look exactly like this one. All right? All right, let's do an example on this, just to compute something, to find something. Okay. Here is the problem. The spacing between the plates of a parallel plate capacitor, so the key word here is parallel plates. Since it's a parallel plate capacitor, feel free to use this, right? Feel free to use C is epsilon naught A over D, because it's parallel plate, so we can use that. Okay, it says the spacing between the plates is 0.05 millimeters. Okay. That's 5 times 10 to the minus 5 meters, right? It's millimeters, so you divide by 1,000. If the capacitance, if C is 1 microfarad, so that's not, it's not 1 farad, it's 1 micro, and we know the keyword micro is means 10 to the minus 6, right? Okay. Good. The first question says find the area of the plates, meaning of each plate, how much area, what is A? So let's start with part A. So we know that capacitance is epsilon naught A over D. Therefore the area will equal to capacitance times D divided by epsilon naught, right? Capacitance times D over epsilon naught. And we can find the area now, so you can say, all right, the area equal to epsilon, capacitance is 1 microfarad, so 1 times 10 to the minus 6. D again is 0.05 millimeters. You have to divide by 1,000 to convert it to meters, so times 10 to the minus 5 meters. Divided, yeah, D is on. I started looking at this one for some reason. And then this one is epsilon naught, so 8.85 times 10 to the minus 12. So this gives me the area. Let's try to get the area. Give you a moment. Again. Five point six four, yeah. At 5.65.
Yeah.
Okay. So 5 something. 5
Meters.
square meters, yeah. Yeah, it's an area. Yeah. B. So to B, it says, find the charge on each plate, assuming the voltage, the potential difference between the plates is 1.5 volts. So when you calculate Q, one plate will have that positive Q and the other plate will have what?
Negative.
The negative of it, yeah. So that's understood, right? When I say the charge, don't say the total, like if you add both plates, how much charge is there?
0.
Yeah, so it will always be 0 in that case. So what we mean by Q is the charge on the positive plate, right? Or the absolute value of the charge. All right, so let's do it. I have capacitance, and so what should I do?
Use that one.
Yeah, use that one. The definition of capacitance. C is Q over V. So C is Q over V, so Q will be CV. Yeah, so Q will equal to C times V. The book always uses delta VC to mean the voltage difference between the parallel plate capacitor. So, all right, I'll put VC. C is, we said, how much was it? Yeah, 1 microfarad, 1 times 10 to the minus 6. And then the voltage is 1.5, right? So this is 1.5 times 10 to the minus 6 coulombs. So I'll just say 1.5 microcoulombs. That's the charge. So 1.5 microcoulombs. Okay. Great. Now, so let's do this from here. Now a capacitor will start usually uncharged, usually not charged. So how do you charge it in the first place? So the way to charge it, you have two parallel plates, two sheets, okay, two parallel plates. You remove one charge from this one and you put it on this one. So if I remove an electron from this one and place it on this one, this becomes net positive since I removed the negative charge from it. And I put an additional negative on this one becomes net negative. And keep doing the process. The only problem is you can't reach in with your hand and do it. So that's where a battery comes handy, and it starts to, you can use it to charge the capacitor. So it looks like this. I'm going to raise this one and lower the other one. So charging a capacitor, it looks just like this. I just want to mention the voltage of the capacitor. So you have a battery. Remember the symbol for a battery looks like this, right? And what are these?
The wire.
Positive.
Yeah, and what's this element here that I drew?
Oh, that's the current?
Like a wire, right?
Wire.
Yeah, a wire. Yeah. And so this is the plus side of the battery, this is the minus side. And then, by the way, you can draw your wire as curly as you like, but I like to draw straight lines. It doesn't matter, right? Whether your wire is straight. Yeah, good. So, looks like that. This, here's my capacitor. That's my capacitor C. And by the way, this is called, we can do something like this. This is called a switch. So it's like a switch. If you open the circuit, the current, the charges cannot flow. They don't have a path to jump from here to here. They can't go through the air. Right? It's an air, that's air vacuum. Perfect insulator, can't jump. So when you close the switch, now charges can start to flow. You got pluses here, you got minuses here. Charges can start to flow. Right, is that clear? So how is the process of charging? Now if there's, later we'll have a resistor, and that slows down the charging process, and it would be like an exponential function. But for now, this process, as soon as you close it, it basically happens instantly, like a nanosecond. So let's close the switch. Again, this is not charged yet. So you close the switch. Okay, what happens? You got pluses here. Let's say a plus goes here, or a minus goes here. So you put the first charge. That costs, remember, nothing, right? It doesn't cost anything when you put the first charge, because it's not met with any resistance. Nobody's there to repel. Now the second charge is that much harder. You put the second charge, well, there would be another positive here that doesn't want to get there. But the battery can pump it and push it through, okay? But this process can only happen up to a certain point. So let's see when the capacitor is now fully charged, what it means to be fully charged. So let's say now the charges stopped flowing, okay? They stopped flowing. So if they stop flowing, I know this. Let's say this is the voltage through the battery, or we can put V battery, VAT, the voltage across the battery, and here is the voltage of the capacitor. Let me put C here, and then from here to here is the voltage across the capacitor, the capacitor, okay? So let's see what we get. Remember the following. What's the potential difference between one point and itself?
Zero.
Go back to the same point, the potential does not change, so 0. Yeah. So let's start here. You can choose anywhere. I like to start right below the negative plate of the battery. Wires are conductors, they're equipotential, there is no potential change. When you jump the battery, when you go from the minus to the plus, by how much does the voltage change? By the voltage of the battery, right? If it's 1.5 volts, then this spot is 1.5 volts higher than this one. Okay, so 1.5, let's say, or V battery. So the voltage has increased by 1.5 volts. Conductor, right? Nothing happens, no change. 1.5, 1.5, 1.5. Now I get to the capacitor. When I jump from here to here, when I go across the capacitor, what happens to my voltage?
Goes down.
It drops, right? It drops, because if I go from here to here, it increases, but if I go from here to here, it drops. By how much? By the voltage across the capacitor. So I get this, V battery minus the voltage across the capacitor, nothing, 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 and I came back to the same spot. What did we say the total change must be?
Zero.
Must equal to 0. This means when the capacitor is fully charged, then the voltage of the capacitor will equal to the voltage of the battery. Okay? And the way you can think of it is, when it's fully charged, the battery is trying to push charges on it, but the capacitor also is full of charges, trying to push them back on the battery. And it's fully charged, that both of them have the same potential, it's like 2 water pumps going against each other, and it just doesn't, none of them, they're equal in power, okay, or in strength. So, long story short, when a capacitor is charged, this is the voltage. Okay? All right. Now, if you only have one capacitor and a battery, end of story is that the voltage in the capacitor will just be equal to the voltage of the battery. The charge on it will be C times V, right? C times V, because C is Q over V, so you multiply C by V, you get Q. And that's the end of the story. Well, fortunately or unfortunately, we combine capacitors. We put them together. You put them in 2 main ways, not the only 2 ways, but mainly these are the 2 ways. Series and parallel. You can put a capacitor next to a capacitor next to a capacitor in a certain manner. So let me show you what we mean by parallel and series. So combining capacitors, let's start here. Let's start with parallel. So here's how it looks like. Suppose this is the battery, right? This is a battery, and that's the symbol. Again, for a capacitor, the 2 plates will be equal in size, the 2 bars will be equal in size, right? The same length. And a battery, one side is longer than the other. The longer one is usually given the plus, and the shorter one is just both the minus, okay? So this is our battery here, and I would have my capacitor here. So this looks exactly like this one, right? Okay, so let's call this one here capacitor C1, and this is the voltage of the battery. Now, if that's the case, then it's the same as here. But that's not. We're going to add another capacitor here, and we're going to call it C2. And we can add a third capacitor here. We can call it C3, and we can add the 4th one and so on. This combination is called parallel. All right? This combination is called what? Parallel. Now, the special thing about parallel, the parallel combination, is that the voltage across capacitor 1 is equal to the voltage of the battery. you see the two wires from the battery touch the two terminals of capacitor 1. And so C1 will experience the whole voltage. C2 will also experience the whole voltage. And C3 will also experience the whole voltage. So that's the obvious way. Here's the more complicated way if you think about it. Do the loop rule. If you choose any closed loop, what's the change in potential?
0.
0. So you can choose this loop, for example. Let's include only this capacitor. Start here. By how much does the voltage increase?
The V back.
V battery. Follow this path. So as long as I'm on a wire, nothing happens, nothing happens. I get here and then I go here. It drops by the voltage of the capacitor. And then I come back here. So that means V battery minus the voltage across capacitor 1 will be 0. So the voltage across capacitor 1 will equal to V battery. Now let's do the second loop. I start here. I go from minus to plus, so I jump by V battery. Keep following. I'm going to use this loop now. So I go from here to here. I drop by whatever the voltage is across capacitor 2. Keep following through. I get back. That means V battery minus the voltage across capacitor 2 is 0, so the voltage across capacitor 2 and the voltage of the battery is the same. So that's the idea. So when they're in parallel, they all have the same potential difference. They have the same voltage. So this is called parallel. And that means, so basically it says V1 is equal to V2 and it's equal to V3. And so on. If you have a fourth one, a fifth one, you keep equating them. That's all. Now, series, on the other hand, is slightly different. So let us deal with parallel first, and then we will do series. Now, for yeah. Any questions?
So C1. So if you were looking at C2, C1 does not affect the voltage of the battery at all.
No. Yeah, the battery eventually will die, right?
Yeah.
But let's say the battery will supply us a certain amount of voltage, and it's while it lasts. Okay. Yeah. So let's say it doesn't die. I mean, reality, yeah, of course it will die. Yeah. Alright. But yeah.
But I mean, like but like I'm saying, like, you know, if you're looking at the C2 loop,
yeah,
C1 doesn't affect the sort of voltage thing, or?
Oh no, it does not.
Okay.
You can, because if I take any closed loop, doesn't matter which loop, the change in voltage has to be 0.
Okay.
Yeah.
Okay.
So the answer is no, it does not. In series, it will. We will see why when it's in series. Yeah. So there is the concept of the equivalent capacitance. What do capacitors do? They hold charge, right? So the whole reason is you charge a capacitor, and then it has charge in it, and then later you can discharge it to get some energy out of it. We'll do that in the next chapter. But the idea of the capacitor is it holds charge. So how much charge do this combination of capacitors hold? And if I were to replace them by just one capacitor, what should its capacitance be? So meaning this. Let's say I want to replace all these 3 capacitors that are in parallel by just one capacitor, and that one capacitor will hold the same amount of charge. What should it be? What should that capacitor's capacitance be? So in other words, this. So suppose I change my circuit into this. Here is the battery, and then I put just one capacitor. We usually call it C equivalent. C that's equivalent to these guys. So it's equal to C1, 2, 3, this combination. All 3 of them. I want to replace them by one capacitor. What should it be? Which is the voltage. Well, you got charging capacitor 1 plus the charging capacitor 2 plus the charging capacitor 3. That total charge, I would like it to equal to the total charge in this equivalent capacitor. Let's see what happens. So I'm going to the next board. So here's what I want. I want this. The charge in the the total charge, which is the charge in capacitor 1, plus the charge in capacitor 2, plus the charge in capacitor 3, I would like it to equal to the charge in this equivalent capacitor, right? Okay, so now for this equivalent capacitor that's connected to the battery, how much charge will it have? Q, and Q is equal to, how is it related to the voltage on the battery or on the capacitor? And the,
C times V?
it's CV, yeah, because capacitance is capacitance is Q over V, so C times V will be the total charge of that equivalent capacitor. So the voltage of the battery will equal to the voltage of this equivalent capacitor, right? When you just have one replacement. So so you would have this. Q will equal to C of this equivalent capacitance times the voltage across this capacitor. What's the voltage across that capacitor in this case?
V battery.
Yeah, it's V battery. So let me put V battery. Okay. Now, capacitor 1, the charge on it, would be C1 times V1, right? The voltage across capacitor 1. But what's the voltage across capacitor 1?
V battery.
It's V battery also, right? Yeah. So V battery. Maybe I should have V1 equal to V2 equal to V3, and all of them are equal to V battery, right? Similarly for 2, so C2 V battery plus C3 V battery. So you can divide out the V battery, right? Then you get C equivalent equal to C1 plus C2 plus C3. This is in parallel, or which case is this?
Parallel.
Series now. Let's do series. So series looks like this. I have a battery, and then I have, as the name implies probably, so you got C1 connected to C2, connected to C3, and obviously you can have a C4 and a C5 and so on. C3, throw the battery in the middle here. This is the voltage of the battery. Now,
This is series,
this is series, yeah. Yeah. I should have taken that. So series now. Series. The all capacitors initially are not charged, and then you connect them to a battery, so they start to charge, right? So this is again the plus end of the battery, this is the minus end of the battery. And the question is, if I were to replace all these three capacitors by one single capacitor that does exactly the same job they do, what should it be? Let's do the voltage change first and see what it is. Let's start here and then go around. So if I go from here to here, what's the potential difference change?
V
V battery, yeah, it increases by V battery. Now I go around, by the way, this is the plus, so this side here will be plus, and this side, oh yeah, let me go through that reasoning first, I forgot that. So before you start them, as soon as you close the circuit, pluses will, let's say, start going here, right? So let's say you put your first charge here, this is a plus. Now, notice this plate here, this shape that looks like an H or a dumbbell, this one? It's not connected to anything. It's not connected to anything. So it starts neutral, and so the total charge on it at the end has to also be still zero. Does this make sense? This little shape here, this one. Yeah, this one is not. Yeah, this one. It doesn't connect to anything. I can just remove it, right? So it starts neutral, and it's not connected to anything. See, this one gets positive because it's connected to the battery, so actual charge will flow on it. and will be added. So how about this one? How is it going to be charged? Well, if you have a plus here, what does a plus do? It attracts a minus, right? So it will attract a minus. Well, where does this minus come from? If it came from, well, it has to come from within, right? If a minus is attracted here, what happens to here? It becomes net plus. And if you have a net plus here, and again, this one is not connected to anything either. So this plus will attract the what here? A minus, and if this one becomes a minus, it must have come from other parts here, so this one becomes plus. And this one gets negatives from the battery. And you can repeat the process over and over. Every time you put a charge here, it attracts another one, and so on. Okay, so now they are charged. This is plus, minus, plus, minus. All right, so let's do the process of going around the loop. You go from here to here. The voltage increases by what again? V battery, right? Okay. And now, let's see. We go from here to here. What happens to the voltage? It drops. Because we went from plus to minus. Is that a hand?
Yeah. When you say we go from here to here, what is we? Is that like?
Let's say by we, let's say an integral. I'm integrating remember what the potential difference, the definition is E dot dr, right? The electric field dot dr. And here I'm integrating over a closed loop, and this closed loop starts here and follows this path.
Oh, so it's just the value of voltage then?
Yes.
Okay.
Yeah. And so if I start here and go around the loop, and I ask what is the change in voltage, it will be zero.
Yeah.
So I guess the we is not like we literally.
Yeah.
So we go, here we go again. Using we. I'll keep using it. I think it's obvious what I mean. Okay. So you go from here to here. It increases by V battery. Then, all right, we get from here to here. What happens?
We decrease.
We decrease. The voltage drops by a voltage V. Since this one is called C1, I'm going to call it V1. And then from here to here, it drops by V2. And then from here to here, it drops by V3. And if there were additional capacitors, it will drop by some more. And nothing, we got here. So what should I put here? Equal to what?
Zero.
The changes, yeah. So that means this. V battery is equal to V1 plus V2 plus V3. Plus V3. We're almost there. Almost there. Let's erase this. Now, I want to replace all these capacitors by just one capacitor. So, what is special about them in series? The total voltage across them will equal to the voltage of the battery, right? Now, the charge on each capacitor will be the same. Because remember how we charge them. As soon as you put a Q here, this becomes a negative Q, and this becomes a plus Q, and this becomes minus Q, and this becomes a plus Q, and this becomes a minus Q, all the time as you charge it. So when you get to the final charge, if this one has a total charge positive Q, this one would also be plus Q, this one would be plus Q. So they would all have the same charge. So in series, what's special is this. Q1 equals to Q2 equals to Q3, and they're equal to just the total charge. That's the total. Now, if I were to replace them by another capacitor that looks like it, the situation then will look like this. I have just one capacitor, this is V battery, and this is C equivalent. That's the equivalent capacitance. What should it be? Well, let's see. What's the relationship between V and Q? What's the relationship between V and Q?
V equals Q over C.
Yes, yeah. So V battery, if I were to replace them by just one equivalent capacitor, the charge of that equivalent capacitor
One
will
over
be Q,
C.
and it's equal to
1 over C1 plus 1 over C2.
would be, V would be Q over C?
Yeah.
Okay, yeah, all right. Okay. So Q over C, yeah, so Q over C. Equivalent, right? So this one, we're talking about this one here. And now, V1, V2, and V3, so it would be Q1 over C1. So it would be Q1 over C1. But why don't I bother with Q1? I just put Q.
Because they're all the same.
Okay. And then for Q2 would be also Q over C1, C2, and Q over C3. And you can cancel the Q's.
One
And
over
so,
C1.
Huh?
1 over C1 plus 1 over C2.
Yes, 1 over C equivalent will equal to 1 over C1 plus 1 over C2 plus 1 over C3. So in series, to find the equivalent capacitance, you have to add the reciprocals first and then do 1 over. And we'll do an example of this in a second. All right, so, yeah. The next, so of course you can combine now a circuit, make a circuit with series combination, a parallel combination, and you combine them together, yeah.
Can you move the board up a little bit?
Yeah. This one?
Yeah.
Let me move the table.
Oh.
That might be better. Yeah. I will write down the product. Example.
Oh, 100%.
So we have a battery here. C1 is 3 microfarads. Here's the question. Find Q1, V1, Q2, V2, Q3, and V3. Meaning the charge and potential difference across each capacitor. Alright? So let's find the charge and potential difference across each capacitor. Now notice, you got, these two are in what